Bismillahirrahmanirrahim. In this video, we are going to study DC motors introduction, its equivalent circuit and types. The previous video also explains about the DC machinery fundamentals and introduction and commutation. And now in this video, we will study the equivalent circuit and types. First, that the DC motors are driven from a DC power supply. And nowadays, induction motors are more important than DC motors because of the invention and highly research done on power electronics and solid state drives. So because of this research and intensive excessively research done on solid state rectifiers and inverters, the induction motors got more importance than DC motors. Now the speed regulation of DC motor is given as we already studied that speed regulation in synchronous generators, induction motors. The speed regulation is speed of no load minus speed of full load divided by speed of full load multiplied by 100%. So it will give speed regulation. Now equivalent circuit of a DC motor. Equivalent circuit of a DC motor can be derived as this is the field coil, this is the field coil resistance, and this is its inductance, which is denoted by LF, and this is the small resistance which is adjustable to control the field current, and this is VF. This is the field circuit, and this one is the armature circuit, in which armature voltage is represented by EA. Then voltage drop occur on brushes, and then resistance, armature resistance, applied V terminal, and this is armature current. So that's how the equivalent circuit of a DC motor looks like. Armature circuit is represented by an ideal voltage source EA and a resistance RA. This is EA and a resistor RA. The brush voltage drop is represented by a small battery VE brush. This is which opposing the direction of current flow in the machine, as its direction is opposing the direction of current flow. The field coils which produces the magnetic flux, these are the field coils which are producing magnetic flux in the DC motor, are represented by inductor LF and resistor RF. This a separate resistor is added to control the amount of current in the field circuit. This field circuit generates the flux. Now flux is present in the DC machine, and now DC current and voltage is applied to the armature circuit on the rotor, and when this is applied to the rotor, current is present and flux is also present. The third thing is rotation and speed, and motor starts rotating. There are few variations and simplifications of this equivalent circuit. One simplification is that we can ignore this V brush, as V brush value is very small in some cases, and this adjustable resistance sometimes lumped up with RF, and now the equivalent circuit of DC motor is simplified and looks like this. That this is the field circuit, this is its resistance, inductance, armature voltage, and now V brush is sometimes ignored or either approximately added some resistance in RA so that this voltage can be encountered. Internal resistance of the field coil sometimes lumped together with the variable resistance, and the total is called RF. The internal generated voltage in the DC machine is given as, you already studied this in previous video, which is in chapter 8. EA is equal to K phi omega, and the torque induced of this DC machine is given as K phi IA. There are 5 different types of DC motor. The first type is separate, which is given here as separately excited DC motor, shunt DC motor, permanent magnet DC motor, the series DC motor, and compounded DC motor. Now one by one we will study these types of DC motor, and the first one is separately excited DC motors. The equivalent circuit of a separately excited DC motor is given as this, which we draw before, is resembled to the separately excited DC motor. What is separately excited DC motor? A separately excited DC motor is a motor whose field circuit, this one, is supplied from a separate constant voltage power supply, is supplied from other source. It means that its field circuit is supplied from other source and its armature circuit is supplied from another source. This circuit is supplied from another source to generate flux, and then this is the V terminal, and IL supplied from an other source. If I am going to draw here the equivalent circuit of separately excited DC motor, it will look like same as I draw before. This is R adjustable. Sometimes these two we lumped for the simplicity. And now this is the armature circuit. This is IA, RA, IF, VF. This is supplied from some other source, and this is supplied from some other source. So this IF is equal to this VF divided by RF, and this VT, this is this one voltage, this one is equal to EA, this voltage, and this voltage drop, EA plus IA RA. And the last one, the line current, which is this line current, terminal current, is equal to the armature current. So the second one is shunt DC motor. The shunt DC motor equivalent circuit is shown in this figure. And what is shunt DC motor? A shunt DC motor is a motor whose field circuit, this one field circuit, gets its power directly across the armature terminals of the motor. If this is the armature voltage. There is no separately voltage or current supplied to the field circuit. This is RA. So this is the V terminals applied to the voltage applied to the armature winding, and this is the armature current, this is the line current. So this is the field circuit. So this field circuit directly gets the voltage and current from the armature voltage and current. If this is all adjustable, this one field resistor, this was inductor, and this one is oil field. So for these motors, shunt DC motor, there is only one power supply which supplies current to the armature circuit and also to the field circuit for generation of flux. So its IF is given as, this is IF, this is equal to VT divided by RF, and its VT is given as, if this is VT, it is equal to same IA, RA and EA. EA plus IA, RA. And now line current, this is the line current, is equal to IF plus IA. So this is the equivalent circuit of shunt DC motor. When the supply voltage to a motor is assumed constant, there is no practical difference in behavior between these two machines. Between separately excited DC machine and a shunt DC machine, there is no practical difference. Their Kirchhoff voltage law is also same. Now the next motor is permanent magnet DC motor. Permanent magnet DC motor is that motor in which this field coil is absent, and instead of field coil, permanent magnets are used. Permanent magnets are used to generate flux which is required for the rotation. So a permanent magnet DC motor is a DC motor whose poles are made of permanent magnets. Now these permanent magnet motors have also its advantage and disadvantage. What are its advantages? Number one is, as there is no field circuit present in this machine, so there is no losses occur across this resistance. So low copper losses on field circuit. And second advantage, as there is no field winding, this field winding present in the motor, as no field winding is present in motor, so its mean its size is smaller than shunt motors and other motors, because there is no field winding present on this motor. So these are the two advantages of PMDC, and PMDC also have some disadvantages. Number one disadvantage is that the permanent magnets are present, and because of permanent magnets cannot produce high flux density. if cannot produce high flux density, and we know that torque induced is equal to K phi Ia, and if this one value is small, so torque induced is small. So in PMDC, the same rating of motor produces small torque. So a PMDC motor will have a lower induced torque per ampere of armature current Ia than a shunt motor of the same size and construction. And its second disadvantage is there is a risk of demagnetization. Risk of demagnetization. For example, as the flux is produced by permanent magnets, and this nature of permanent magnets can be changed during heating. For example, if motor is running continuously overloaded and motor heat up, so this nature of permanent magnet may some change, and this flux value will change, and it because of heating this demagnetization will occur. As we already study same thing in transformer. During transformer we study that which things affect the saturation. Second risk of demagnetization can be occurred by the armature current. If the armature current becomes very large, there is some risk that the armature MMF may demagnetize the poles. For example, if armature current have its own magnetic field, this magnetic field may interacts with the magnetic flux of permanent magnets, and thus at some point it increases the flux, and at some point it may demagnetize these permanent magnets. So there is a risk of demagnetization in this permanent magnet DC machine. Now the next motor is the series DC motor. As the name suggests that series, it means that the field coil is connected in series, like this is. A series DC motor is a DC motor whose field windings consist of relatively few turns connected in series with the armature circuit. And its equivalent circuit looks like this. If this is the armature voltage, so this series winding and inductance in series with the armature winding. As from the figure you can see, when load increases means Ia will increase, so this Is will also increase, which is equal to Ia, so flux also increases. So in this Ia is equal to Is is equal to IL, and V terminal is given as EA plus IARA, this voltage drop, plus ISRS, this voltage drop. You can see that the flux is directly proportional to the armature circuit, armature current. If current is increases, the current in the field coil also increases and flux also increases. As torque and its torque also increases. Torque induced is given as K into phi Ia. If Ia increases, this flux also increases and torque induced increases. So it means these motors have more torque than the other motors. The flux in this machine is directly proportional to its armature current, and if Flux in the machine is given as phi is equal to CIA. C is the constant of proportionality. The induced torque in this machine is thus given by torque induced is equal to K phi Ia, and instead in phi place CIA and its value will become KCIA square. KCIA square. It is easy to see that a series motor gives more torque per ampere than any other DC motor, and therefore used in the applications where high torques are required. So this is the advantage of series motor, that in series motor can produces high torque than other motors. Now the last one is the compounded DC motor. A compound DC motor is a mixture of shunt and a series motor, in which shunt series winding, shunt field winding and series field windings both are present in this motor, like this. This is the series field winding and this is shunt field winding, and now this motor have both the characteristics of series motor and shunt DC motor. If I am going to draw its equivalent circuit, so its equivalent circuit will look like this. EA armature resistance. Now this is the field winding resistance, field winding inductance, this is shunt winding resistance and shunt winding inductance. So that's how compound DC motor looks like. This is dot on which current is entering. RA, IA, this is adjustable, this is field RF and LF. This dot is adjustable. So that's how the equivalent circuit of compound DC motor looks like, which consists of both the series and shunt winding field. So if current flows into the dots on both field coils, like this dot, like this, and here is also dot, then the resulting magnetomotive force add to produce a larger total magnetomotive force, and this situation is known as cumulative compounding. But if current flows into the dot on one winding and square on the other winding, then the resulting magnetomotive forces subtract, and this situation is known as differential compounding. For example, if there will be no dot here and current enters at the square end and dot at this end, then it is magnetomotive force subtracts each other, and this will become differential compounding. So there are two types, one is cumulative compounding and other one is the differential compounding. And at the end, the voltage is given as EA plus IARA, like voltage drop on this and voltage drop on this, plus IARS, and IA, if this direction is this, is equal to IL minus IF, and IF will become Vt, this is the Vt divided by Rf.